Welcome back to Pacing Equilibrium in the First Price Auction Markets by Vincent Conitzer from Duke University and his collaborators from Facebook CTS. So in this video, we are going to define what is this pacing equilibrium, what are the requirements for this equilibrium, and next we will see that this problem maps to the Eisenberg-Gale convex program, and we'll study the properties of that program that would explain how this mapping happens. But before we get into that, let me emphasize one thing, that there is another assumption about the agents in the system. Basically, it wasn't implicitly assumed in the first video, but I want to make it explicit here. So the agents are budget constrained, and ROAS constrained, value maximizers. This is very important. So what is this value maximizers? The agents in this system, they want to get as much value as possible. So they are really interested in getting as much value as possible. Remember, this is the allocation of the agent I and item J, and this is the value. So this is to be maximized by every agent. And so that the budget constraint holds, okay, subject to budget and ROAS constraints. So this is why this is important, because this means that these agents, they are not linear. A typical linear agent would be maximizing his profits, or which is like surplus, which is the difference between the value acquired in the auction minus the payments that are made to the auction. But here we see something different. We see that the agent is interested in maximizing this quantity, and the payments, they only enter in the constraints. So the payments do not enter the objective function of the bidder. Okay, so now that we're in a position to actually state what is this pacing equilibrium. Okay, so pacing equilibrium is a set. Pacing equilibrium is a set of multipliers BIs and prices PJs and allocations XIJs, so that the following holds. First, given the prices PJ, each agent chooses his preferred bundle of items. So it's basically just the agent proposes the XIJs for this agent I. And in the equilibrium, the total sum of all allocations for particular items are all ones. So in the equilibrium, sum of XIJs over all agents is equal to 1. So this is also known as market clearing condition. It just says that given the correct equilibrium prices, all the agents would buy their preferred bundle given these prices and given their constraints on the budgets and the ROAS, and the market would be cleared. Like all the items would be sold completely, there will be no overselling. Okay. Condition number 2 is no agent is unnecessarily paced. And this means that if the budget, if the agent doesn't spend its full budget, then, and we will see it a little bit later, that the BIs are actually inverse of the ROAS. This is inverse of the ROAS. Right. So this condition says that if the agent has some budget remaining, this could only happen if BI is actually equal over 1 over RI, if there is excess of the budget. Otherwise, BI should be less. If this happens, then the budget is fully spent. Okay. So this is the definition of the pacing equilibrium. We are choosing these BIs. Basically, when we have chosen the BIs, we automatically get the PJs, because remember that PJs are just the maximum bid, and the bid is proportional to values times these multipliers BIs. And given the PJs, we get the allocation Xij in the way that all the bidders actually choose their most preferred bundle of items. And at the same time, no agent is unnecessarily paced. And by this, we mean that if agent has a small budget, it spends it in full, and it may get this multiplier, this inverse ROAS, less than the constraint. But if the advertiser hits the ROAS constraint, then only then it might have some remaining budget. Okay. So it turns out, and it's really probably the most interesting thing here, is that this set of constraints, this definition of pacing equilibrium, could be mapped into the Eisenberg-Gale program. And let me show you what is this. So the solution to this program will give us everything we want. It will give us the multipliers, it will give us the prices, it will give us the allocations, and all of these conditions will hold. So the proof that this equilibrium exists basically follows from the existence and uniqueness of the solution of the Eisenberg-Gale program. So what is this Eisenberg-Gale program? It is the following. We want to Okay, so this is a primal formulation for it. So there will be a function f of xij's in some variable delta I, which will have the meaning of the remaining budget. So this is the excess of the budget. And this is defined in the following way. It's the sum of budgets times logarithm of utility of player I minus delta I. This is sum of over i's over agents, and this is to be maximized. But there are constraints, and the constraints are the following. The UI is less than equals to sum of xij's vij, sum over items, plus ri delta I. So remember, this is the utility of the player I. This is the utility of the player I. And we discussed above that the utility of the player I is the value that he gets from the auction plus the remaining part of his budget. But the funny part here is that he actually values his money at the rate, at this minimum rate, this Ross constraint rate. So for this agent, it is better to save budget if he cannot convert it to value at this rate. So this is the minimum possible rate. Okay, so this is the constraint on the utility. Then we also have the constraint that every item is not oversold. So we have sum of xij's over i's should be less equals to 1. So the total allocation of every item j is no more than 1. We have a constraint on I'm sorry, on remainder of the budget being greater than 0. Okay, so this is it. This is the Eisenberg-Gale program. And to understand how it gives us all the properties that we want and where are those pacing multipliers, we should actually consider the dual program. So this will be the primal program. And now we need to derive the dual program. I will write it out and then I will and then we will derive this. So the dual program. The dual program will be for prices and pacing multipliers. And it will say the following, that we need to minimize the set of prices, Pj's, minus the sum of mi's logarithm beta i's, sum of I, and this to be minimized. And the constraints here are that Pj should be larger than Bi times Vij. So remember, this is the first price auction condition, that the price of the item J should be the largest bid, and this is the bid in our system. Then there is a constraint on the rows, so we will say that the bi should be no larger than 1 over Ri. So this is this interpretation that the bi's are inverse rows. bi's are inverse rows, and this is also known as bang per buck. Yeah, and that's it. This is the dual program. So in the next video, we will actually spend a lot of time deriving this, and along the way we will see that all the conditions that we wanted, they actually hold, and they appear as just the optimality conditions, like the KKT conditions of this program. So let's examine this a little bit. So Eisenberg-Gale program, why is it convex, or in this case concave program? It's because the log function is concave, and this is the linear function. The delta I is just linear function, and all the constraints here are linear constraints. And the dual program is a convex program. Why is that? Because this is a linear term, and linear functions are convex. And this is the logarithm function. The sum of logarithms is, every logarithm is a concave function, but here's the minus sign, so this is negative logarithm. This is convex function, and the sum of weighted sum of convex functions is convex function, and the constraints are linear again. So we can see here that Eisenberg-Gale program is a convex program. And we actually can expect a strong duality in this program. So what does it mean? It means that there will be a set of xij's and delta i's, so the primal variables, that is optimal in the primal program, and there will be corresponding dual variables, pj's and bi's, that will be optimal in the dual program, and the value of these functions, the value of these programs will be exactly the same. Actually, this will only happen, there is additional term here. There is a constant here. And we will derive that constant so that we could actually have this strong duality. And strong duality is really good thing, because if we solve the primal and the dual programs at the same time, there is a certificate that we have found the optimal value, because only in the case of primal and dual programs have exactly the same values. This could only happen if both of them are optimal. Why is this? Is because one of the programs is the lower bound for the other program, and so they can only touch at the optimum.